We are now going to talk about the technique where you basically integrate the Biot-Savart law. And the first step is to think that the Biot-Savart law is only applicable to point charges. Now what we're doing is considering a very tiny piece of current, which is effectively going to be a point charge. So the movement of a chunk of charge, delta Q, is going to be equal to the current times the length that it's moved through. So that picture is kind of shown here. So delta S in this case is just some little displacement vector that our charge has moved over. And remember that current is charge per time. So the units work out here, and we're just either thinking about a current over a length or the velocity of a chunk of charge. So we want to think about this because it shows us then that the Biot-Savart, which had a term of Q times V, well, we can use this to say Q times V is now just equal to current times delta S. So the reason why we want this form now that is Biot-Savart expressed for a tiny segment of wire is that delta S is going to be the differential that we're working over. And this is technically going to be a path integral. I'm not going to go through the math here. It's something that if it makes sense to you, if you've learned path integrals before, it's really not that bad. But if you've never done a path integral before, this is going to be quite confusing. So this is one of the places that I really encourage you to work with tutors if you can't follow what's in the book. It's something that if I explain it, assuming that you don't know anything about this, it would probably take an hour in itself. So I'm not going to go through the details of this, but I'm going to talk about the basics of how to do it in terms of making it analogous to what we did for electric field. So delta S is going to become the differential that we're integrating over, and it represents part of where the wire is. I is the current flowing through it, and then every other piece is just like Biot-Savart before. So the problem-solving strategy that you want to use here is again kind of complicated, but looks just like what we did for the electric field from extended objects. So first, we want to model the wire as a simple shape. Now in this case, you either are doing this because you've been told that you must use Biot-Savart to do it, or it's a simple shape that you don't already know the magnetic field for. If you look at the wire and say, well, I know it's an infinite wire, you maybe don't actually need to do this. So don't feel like this is the only way to get it. Again, this is one of 3 strategies. But you do want to at least simplify its shape a little bit, make it a line. Maybe not a straight line, maybe it's a curvy line, but you typically don't need to think about like the radius of the wire, for instance. Then you need to draw a pictorial representation. Again, just like integrating over an object for electric fields, you really want to make sure that you have a coordinate system, identify the point at which you're actually calculating the magnetic field, and then start breaking your wire into pieces. And think about how you can parameterize that. Do all of the pieces have the same distance from the point? Do they have the same angle? So you might want to choose your coordinate system in a way that will make this as simple as possible. Then you're going to want to draw the magnetic field vector for 1 or 2 segments, right? Actually start setting it up and say, if I consider one segment to be effectively a moving point charge, at point P, what would my magnetic field look like? And you want to set that up for 1 or 2 points, make sure you have a generalized form, and then you start integrating. Now remember, superposition holds here. So what you're really doing is adding up every little magnetic field piece. But because we have a continuous object, that sum is actually going to become an integral. But what's important to remember here is that this is also a vector sum. So you need to consider all 3 directions, x, y, z. Now you might be able to use symmetry to argue that you have 0 magnetic field in 1 or more of them. That's fine, but make sure you're at least thinking about all 3 directions and make that argument explicit. Don't just calculate z and ignore x and y, because then it's unclear if you knew that there is symmetry so that you could ignore them, or if you just forgot to do it and got very lucky. So make sure that you think about that direction from each individual piece. Then try to simplify everything down into a single coordinate that you're going to end up doing your integral over, and then do the integral. Now frequently you are going to have limits of integration to worry about. This is usually going to be a definite integral, so make sure you think about that. In the end, you should be able to look at the answer you got, check that the units work, and there's actually going to be some simplifications that happen just like the electric field situation, but it's a little harder to think through, at least right now. does the functional form of the magnetic field simplify to what I expect if I'm really close or if I'm really far away? That's harder to understand now, but it does actually still hold true.